Thank you very much. Thank you all for being here today. So the title of my presentation is Unveiling the Electronic State Interplay at Titanium Oxide ITIC Electron Transport Layer, Non-fullerene Acceptor Interfaces, and Highly Efficient Organic Photovoltaics. And now we'll just start with some introduction. So yeah, this presentation, the devices that will be mentioned in this presentation are organic photovoltaics. And a very, very important development that happened in the world of organic photovoltaics is the transition from fullerene to non-fullerene acceptors or NFAs. So for a while, fullerenes such as C60, C70, and PCBM were used as electron acceptors in organic solar cells, and they also did really help the development of organic solar cells. As you see here, they did increase the PCE or power conversion efficiency, but it was later revealed that they actually put a maximum limit of around 12% on the PCE, and some of the reasons behind that is because for fullerenes, it's not very easy to tune their energy levels. They also don't have the best absorption across the solar spectrum. So to avoid these issues and to be able to get a higher PCE, this transition from fullerene to non-fullerene acceptors happened around 10, 15 years ago. So non-fullerene acceptors or NFAs, the name indicates that it can be anything that is not fullerene. But usually when we talk about NFAs, we talk about these kind of fused ring organic molecules with an electron deficient core. ITIC is one of the popular ones, and also Y6 that you see here. And some of the benefits of NFAs is that they have tunable energy levels, crystallinity, and optical properties. They're easy to synthesize, and they have better absorption across the solar spectrum compared to fullerenes, and also a better thermal stability, which also will positively affect the stability of devices. And the study I will present today will include ITIC that you see right here. So another thing that is important for this talk is the metal oxides in organic solar cells. So typically in organic solar cells, the active layer, which can consist of a donor and an acceptor, is sandwiched between two charge transport layer, a hole transport layer at the anode side, and an electron transport layer at the cathode side. And often these are made of metal oxides. They can also be made of organic materials, but they're often made of metal oxides because they're non-toxic, cheap, easy to process, and also easy to you can manipulate their optical and electronic properties. And what these electron and hole transport layers do is they basically aid charge transport between the organic active layers and the electrodes due to a favorable energy level alignment at the metal oxide organic interface, which lowers energetic barriers and makes it easier for charges to be transported. Now, metal oxide transport layers can either be electron transport layers or hole transport layers, depending on their electronic structure. Examples of some electron transport layers are zinc oxide, titanium oxide, and tin oxide. And these are often N-type materials with a low work function and a low lying valence band so that they can block holes and be electron selective. And hole transport or hole extraction layers are usually P-type, can also be N-type materials with a high work function, high lying conductance band, and they can also be exciton blocking if they're P-type. And examples of such hole transport layers are molybdenum oxide, vanadium pentoxide, and nickel oxide. And now I will just briefly go through some of the experimental methods that have been used in this study, because they might not be familiar to everybody. So the first technique I will talk about is spiral deposition, and this is a thin film deposition technique that requires a UHV environment, so is done in a UHV chamber. And in this deposition technique, you have a sputtering target, which is made of the material that you want to make your thin film from. This target has a negative bias, and sputtering also requires the presence of an inert gas, and very often it's argon that is used. So the sputtering target is bombarded by positively charged argon ions with very high velocity and very high kinetic energy. And when they hit the surface of the sputtering target, this causes some atoms to be ejected, knocked off, or sputtered off the target surface, and they move through the vacuum chamber where they cover a substrate as a film, as a thin film. It's possible to do sputtering, where you let in a reactive gas, such as oxygen or nitrogen, and this will alter the final composition of the film that is created, and this is called reactive sputtering. Some of the benefits of sputter deposition is that it is scalable and is compatible with large-scale printing techniques such as roll-to-roll processing. In our group, we often use sputter deposition to make electron and metal oxide electron and hole transport layers, because we have shown several times that the sputtering allows for a flexible tuning of the optical and electronic properties of these thin films and microstructure and the work function. So you can use it to tailor the properties of your metal oxide to fit in your device. Another deposition technique that has been used in this study is spray deposition. And spray deposition is a way to deposit a thin film from a solution in a vacuum. So the spray deposition tool that we have used in this project has 3 vacuum stages. And then the third stage can be connected to a deposition UHV chamber. So you start with your solution that you want to make a film of. You put it in a capillary, in a syringe, and then it is sprayed into a capillary that lets it into the first stage of the spray deposition tool. The first stage is in a low vacuum. Then the solution moves through the first skimmer cone to the second vacuum stage, which is in a bit higher vacuum than the first stage, and then it moves through the second skimmer cone to the third stage, which is in an even higher vacuum. And finally, the solution is sprayed into the deposition chamber where it covers a substrate as a film. So the main technique that has been used in this study is X-ray photoelectron spectroscopy, or XPS. And as the name indicates, it is an X-ray-based spectroscopy technique. It is a very surface-sensitive technique, so it provides information about the first 1 to 10 nanometers of a surface. So it is perfect for studying thin films. So in this technique, a surface is hit by X-rays. The incident photon energy of these X-rays is either equal to or higher than the binding energy of a specific electron in a specific orbital, which results in this electron being emitted as a photoelectron. Now, the detector of an XPS tool, it detects the emitted photoelectrons and discriminates between them based on their kinetic energy. So they each have they have different kinetic energies. And the kinetic energy is used to determine the binding energy of these electrons. The binding energy is related to the kinetic energy by this relation. So the binding energy of a photoelectron can be calculated using the incoming photon energy of the X-rays, the kinetic energy of the photoelectron, and the work function of the spectrometer, which is an instrumental constant. The binding energy can provide information about which element the photoelectron came from, which energy level in that element it came from, and the chemical environment that it was in. Another X-ray-based characterization technique that was used in this study is near-edge X-ray absorption fine structure, or NGSE for short, and it is an X-ray absorption spectroscopy technique. As the name indicates, it provides information about the fine structure close to the absorption edge. In this technique, you also have a surface that is hit by some incoming X-rays, but in this case, the energy of the X-rays, the photon energy of the X-rays, is either equal to or slowly below the vacuum energy. So therefore, the emitted electrons cannot leave the material, but instead they will be excited to an unoccupied level. This means that NGSEs can give us information about unoccupied level in the material, while XPS only provides information about occupied levels such as core levels and valence bands. Now, because NGSEs, it requires you to be able to tune your photon energy. It cannot be conducted using normal X-ray sources that you would find in your own lab, but it requires the synchrotron radiation. Then there is the last technique I will be introducing is resonant photoemission spectroscopy, or RESPES, and it is a combination of X-ray absorption spectroscopy and photoemission. So basically, RESPES is a way of doing selective photoemission enhanced by resonance. And what this means is you do an XPS measurement, but you tune your photon energy to match the absorption edge of a specific core level. And by doing that, you enhance the XPS signal of that core, of a specific core level. So the study I will present today will be, well, a surface study of the titanium oxide ITIC interface, but this study was inspired by a device study also from our group. So I will just briefly go through that study first. This study is called Enhanced Long-Term Stability in NFA-based OPVs with sputter-deposited titanium oxide electron transport layers. It is a part of a paper, this paper that is currently under review. So the background for this study is, well, one of the most widely used metal oxide electron transport layers in OPVs is solution processed zinc oxide. And some of the reason behind that is, well, it has some desirable properties such as a high electron mobility and low work function, but also it can be processed at low temperatures, which makes it compatible with flexible substrates such as PET films. However, it has been shown that for non-fullerene acceptor-based devices, solution present zinc oxide presents some challenges and which limits the long-term device stability, and that is because solution present zinc oxide has a large concentration of surface defects and a strong photocatalytic activity. So when it is exposed to UV light, it results in a photocatalytic degradation of NFA molecules, which, as you can imagine, limits the long-term stability of devices. So these issues can be overcome by, for example, trying to passivate the surface defects in solution present zinc oxide and thereby passivate this effect, or by replacing solution present zinc oxide with another metal oxide ETL. And this is what has been done in this study. So we have basically replaced the zinc oxide in NFA-based OPV with the sputter-deposited titanium oxide. So these are the devices that were made. So we use PC12 as a polymer donor and ITIC as an NFA. And then the devices either had solution processed zinc oxide or titanium oxide as an ETL. Here we have the JV characteristics for both, and we see that the initial device performance is quite similar for devices with both ETLs. The maximum PCE was 10.6% with the zinc oxide and 10.3% with the sputtered titanium oxide. But then if we look at the stability study, so this is the stability of encapsulated devices in air at room temperature that were continuously exposed to one sun illumination. And if we look at the initial stability, we see that the burn-in degradation is quite similar for both kind of devices, and that is probably just due to the initial degradation of the active layer materials themselves. But then if we look at the long-term stability, we see a significant difference. We see that for the devices with the solution present zinc oxide, they saturate at around 35% of their initial PCE after 14 days of degradation, while the devices with this sputter-deposited zinc oxide, they saturate at around 60% of their initial PCE after 14 days of degradation. So there is a significant enhancement of the long-term stability of these ITIC-based devices when we switch from solution present zinc oxide ETLs to sputtered titanium oxide. So to try to understand why this is the case, we did a degradation study of ITIC on solution present zinc oxide and ITIC on the sputtered titanium oxide. So the ITIC was degraded for 20 days following the ISIS L1 protocol. And if we look at one sunlight, and if we look at the absorbance spectra that we have here, we have the absorbance spectrum of the degraded ITIC on zinc oxide and on titanium oxide. We see that the main absorbance signal from ITIC is significantly reduced after 20 days of degradation when it is deposited on the solution present zinc oxide. And that shows this UV-induced photocatalytic degradation of ITIC by zinc oxide. But this effect is almost fully mitigated at the titanium when the ITIC is deposited on the titanium oxide. So this indicates that the sputtered titanium oxide does not have a strong photocatalytic activity and therefore does not result in this strong photocatalytic degradation of ITIC, which is seen when ITIC is on solution present zinc oxide. But this is actually a quite surprising observation because titanium oxide is known to have a strong photocatalytic activity, and it is used in photocatalysis. So the question from this that we then had after this study is, why is this the case? Why is our sputtered titanium oxide not degrading the ITIC? Why does it not have a strong photocatalytic activity? So this leads us to the study that is the main point of today, which is the surface study of the in-situ prepared sputtered titanium oxide ITIC interface. So we took our sputtered titanium oxide and we went to the Max IV synchrotron in Sweden, together with Professor Nadine Witkowski from Sorbonne University, to study the interface between the sputtered titanium oxide and ITIC. Namely, we studied the electronic state interplay at this interface and defect states to try to understand why we don't see this photocatalytic degradation of ITIC on the sputtered titanium oxide, and why this titanium oxide has a reduced photocatalytic activity. So we went to Max IV to this beamline that's called FlexPass, which is a beamline where you can do XPS and X-ray absorption spectroscopy. And we did XPS, NEXUS, and RESPES measurements on the sputtered titanium oxide before and after deposition of ITIC. So something else that is new and interesting about this study is that we actually deposited ITIC in situ at the beamline without breaking vacuum. So basically, we used spray deposition to deposit ITIC in vacuum on the titanium oxide, and then we moved it to the measurement chamber without breaking vacuum. And this is quite new because often when such studies are done on non-fullerene acceptors, they are prepared ex situ, for example, by spin coating, and then they're put into the measurement tool. So what we did is we mounted our spray deposition tool to the load lock right here, did our spraying of ITIC on top of the titanium oxide, and then we just moved the samples here to the experimental chamber where we did the photoemission and absorption measurements. And the results that we got, we compare them to similar measurements done on the titanium oxide that is an anatase single crystal, because anatase titanium oxide is known to have a very strong photocatalytic activity. So it's a good reference for our titanium oxide, which does not have a strong photocatalytic activity. So here are the XPS. I will start with the XPS results of the sputtered titanium oxide before and after deposition of ITIC. And here we have the titanium 2P core levels. So if you look at the titanium oxide, sputtered titanium oxide before deposition of ITIC, we see that we have, for the titanium 2P3 we have two features, a large main feature at 459.2 electron volts, which corresponds to titanium 4+, that is dominating. And then we also have a small shoulder at lower binding energy, which corresponds to reduced titanium 3+ species. Then we deposited three different thicknesses of ITIC on the titanium oxide, 0.5 nanometers, 0.9 nanometers, and 1.8 nanometers. And one thing we see is we do not see any major shifts in the titanium 2P main peak after deposition of ITIC, but we do see a strong reduction of the amount of titanium 3+ upon ITIC deposition, and this indicates oxidation of titanium 3+ upon ITIC deposition. Here we have the oxygen 1s core levels, also for titanium oxide before and after ITIC deposition. And before deposition of ITIC, we see three features: one main large feature, which can be attributed to oxygen bound to titanium 4+, or what is also called lattice oxygen, and then a shoulder at slightly higher binding energy corresponding to adsorbed OH defects, and even smaller defect peak, which is from adsorbed water. After deposition of ITIC, we actually see that a new feature emerges, and this is due to the oxygen in ITIC, because ITIC does also have oxygen. And then when we increase the thickness of ITIC, this feature moves towards higher binding energies. Here we have the carbon 1s core levels, also for sputtered titanium oxide before and after deposition of ITIC. Before deposition of ITIC, we do see some carbon, which is just carbon contamination of the surface, because the titanium oxide was exposed to air before measurements. But then after deposition of ITIC, we see a main peak. A main carbon 1s peak, which corresponds to carbon bond to carbon, and then also a shoulder at higher binding energy. And when we increase, similar to oxygen, when we increase the thickness of ITIC, the carbon 1s main peak shifts towards higher binding energies. Here we have the valence band spectra for the titanium oxide before and after ITIC deposition. And one thing that we see is that the valence band maximum shifts closer to the Fermi level upon ITIC deposition. But something also interesting to note is that we see for the titanium oxide before deposition of ITIC, we see this feature around 1 electron volts above the Fermi level. And this is a feature this is the defect state, that is often observed in the valence band of metal oxides, and it's coming from excess electrons partially filling the titanium 3D states in the surface and subsurface region due to oxygen vacancies. So basically, it is a defect state related to oxygen vacancies. And after deposition of ITIC, it is attenuated, but if we zoom in, we can see that it is still there. It's not fully quenched. So, summary of the titanium oxide ITIC interface based on the core levels and valence band spectra. What we see is we have after deposition of ITIC, the deposition of ITIC does result in an oxidation of the titanium 3+ species in the titanium oxide, and also that when we increase the thickness of ITIC on the titanium oxide, the oxygen 1s and carbon 1s peaks for ITIC shift towards higher binding energies, and these two things combined indicate electron transfer at the interface between ITIC and titanium oxide. So another thing we did was we did resonant photoemission at the carbon edge, which means that we measured XPS, where we match the photon energy of the incoming X-rays to be equal to the absorption edge at the carbon K edge absorption edge. So to find the photon energy, we had to first do NGSE at the carbon edge, and we see one main feature at 285.2 electron volts, which corresponds to transitions from the carbon 1s level to the pi star level. So then we measured the valence bands for 0.9 nanometer ITIC on titanium oxide at this photon energy, so that is our on resonance spectrum, and then at another photon energy, 282 electron volts. And we see that for the on resonance spectrum, it's very similar to what we saw before. It's the valence bands we saw before. It is dominated almost entirely by the titanium oxide substrate. But then when we look at the on resonance spectrum, it is actually looks very different, and that is because here we are enhancing the signal when we are on the absorption edge of carbon. We are enhancing the signal from the carbon HOMO states. So we see that we have a quite strong feature at around 4 electron volts, and this is a feature that is usually also observed for spin-coated ITIC, a thick layer of spin-coated ITIC. So basically what we have done here is we have suppressed the signal from the titanium oxide substrate, and we have enhanced the signal from the ITIC overlayer itself. Now we see on both of these valence band spectra, we still have this 1 electron volt defect state that I was talking about before. So we know we already know we have it in titanium oxide, but the question is here when we are on resonance, is this feature still only related to the titanium oxide substrate, or is the HOMO states of carbon also contributing? Is there some interfacial state at the interface? So to answer this question, we just subtracted the off resonance spectrum from the on resonance spectrum, and then we get this spectrum where there is no feature at 1 electron volt, which means that this defect state is only related to the titanium oxide itself, and the ITIC, at least the carbon HOMO states from ITIC are not contributing to this at the interface. So another thing we did to really study to really study this defect state further was we did resonance photoemission at the titanium L edge. Now, when you tune your photon energy to match the titanium L edge absorption edge, what you do is you enhance transitions from the titanium 2p orbital to the titanium 3d orbitals. So to find the right photon energy for on-resonance spectra, we did NGSEPs for both titanium oxide before ITIC deposition and titanium oxide after deposition of 0.9 nanometer of ITIC. And the NGSEP spectra look quite similar. We do see two main features below 462 electron volts, which one at 458 electron volts, one at 459.7 electron volts, and they both they both originate from transitions from the titanium 2p to 3d, but one of them shows the transition from titanium 2p to the 3d EG suborbital, and the one at 459.7 shows the transitions from titanium 2p to the 3d T2G suborbital. Now we also did this measurement for anatase titanium oxide, a single crystal anatase titanium oxide, single crystal before and after deposition of ITIC, and we still see the same two features in the NGSEPs. So then what we did for both sputtered and anatase titanium oxide before and after deposition of ITIC is we measured the valence band with these two energies, so two on-resonance energies, and then at 450 electron volts where we are off resonance, so to try to enhance the 1 electron volt defect state, and it worked. So if we look, and it worked for both anatase titanium oxide ITIC and sputtered titanium oxide ITIC. We see that when we are off resonance, this one electron volt defect state is very small, but when we are on resonance, we significantly enhance the intensity of this defect state, and this we see the same here for the anatase titanium oxide. So we chose to go with one of these photon energies, 458 electron volts, and then we zoomed in on this 1 electron volt defect state. You see the zooms here. So here we have, on the top, we have sputtered titanium oxide before and after deposition of ITIC, and on the bottom we have anatase titanium oxide before and after deposition of ITIC. So we wanted to fit this defect state, and we saw that two features for sputtered titanium oxide, both before and after deposition of ITIC, two features are needed to fit this defect state. A low binding energy feature, which corresponds to oxygen vacancies in the subsurface region, and a higher binding energy feature, which corresponds to surface oxygen vacancies. And for sputtered titanium oxide, we have the ratios here. We see that the surface vacancies are strongly dominating both before and after deposition of ITIC. And actually, after deposition of ITIC, the subsurface defects are quenched. So the surface defects are even more dominating after the deposition of ITIC. Now, for the anatase, the situation is quite different. We see, first of all, before deposition of ITIC, there are three features in the anatase. One very close to the Fermi level, which is a shallow bandgap state, which is often observed in anatase single crystals. But then we also have our low binding energy subsurface oxygen vacancies, and then also the surface oxygen vacancies. But here we have a 50-50 contribution of surface and subsurface oxygen vacancies, unlike the sputtered titanium oxide, where surface oxygen vacancies were dominating. And after deposition of ITIC, we still have a 50-50 contribution. So the subsurface vacancies are not quenched after deposition of ITIC for anatase titanium oxide, only for sputtered titanium oxide. And this significant difference actually tells us why our sputtered titanium oxide does not have a strong photocatalytic activity, just like anatase titanium oxide, because the anatase titanium oxide is known to have a strong photocatalytic activity because a large part of its oxygen vacancies are in the subsurface region. And when oxygen vacancies are in the subsurface region, they are less likely to be quenched by surface adsorbate, which allows them to participate in the photocatalysis process. But in the case of the sputtered titanium oxide, where the surface vacancies are dominating, then you have most of your oxygen vacancies are on the surface, so they can be quenched by a surface adsorbate, and therefore they cannot be part of the photocatalysis process. And this explains why our sputtered titanium oxide has a reduced photocatalytic activity, and therefore does not result in a strong photocatalytic degradation of NFA molecules in devices. So just to conclude this study, we saw that at the interface between sputtered titanium oxide and ITIC, there is electron transfer, and we saw that there is a difference between that most of the oxygen vacancies for sputtered titanium oxide lie on the surface both before and after ITIC deposition, which results in a reduced photocatalytic activity, as opposed to anatase titanium oxide, where there is an equal contribution of surface and subsurface defects, oxygen vacancies. And another also important thing, a result from this study, is that we were successfully able to deposit ITIC in situ by spray deposition. So we were able to measure an in situ prepared interface with that is not affected by the surrounding environment. And finally, I would just like to thank everybody from SDU Cape and all of our external collaborators, and thank you all for listening.